So welcome to the fourth lecture. So I don't know, some of the students are sitting behind, so you don't want to pay attention in the class, or it's at the visibility level, maybe. Let's see. Okay, so I hope everybody submitted the first assignment, right? Was anybody not able to finish in time? I know some students have emailed me because of last minute uploading issues, but modulo that, is everybody done with assignment 1? It was an individual assignment, so in case you're relying on somebody else submitting, that's not going to happen. Okay. So how many of you were able to kind of look at the project details and kind of start thinking about it? Yeah, if you want to do an interesting project, so that you can show off to other people and other students and so on after the end of this course, you may want to start early so that you don't do a last minute. Creativity doesn't come at the last minute. So maybe you can read the instructions and think about it. Maybe you'll get some thoughts on how to do something creative here.
Do you have any suggestion on how to find the ideas?
So actually in today's lecture posting on Blackboard, I gave a link to a website that I came across called data.world. It seems to have some interesting data sets that you can explore. So today I'm going to go through one example application. You can maybe draw some inspiration from it or not do anything related to that. So we'll see, and you can talk to both the TAs and me if you depending on your ambitions, right? So yeah. Okay. So today we're gonna start with a couple of applications and then look at several methods, depending on time. So these methods, actually I wrote down a couple of methods last time. I'm going to write down the 4 methods and we're going to go through them in detail. The 4 methods are regression, LASSO, linear discriminant, analysis, and logistic regression. So how many of you thought about using logistic regression in the first question? Okay, so that means you are either aware of in which settings logistic regression needs to be applied, or you have heard it from somewhere or some other course, right? So we're going to cover in today's lecture, what logistic regression is about, what assumptions it's making, and when it's applicable and when it's not applicable. Okay. So these are the 4 methods. Let's see how much we can cover. In between, we will take a detour into a little bit of linear algebra. So I know linear algebra has been a recurring theme in almost all of these lectures. So if you're really not comfortable with matrix vector products, matrix inverses, and so on, you should go through the reviews. I think in one of the lectures, one of the lecture items on Blackboard, I've given a link to review of matrix algebra, right? So have a look at that PDF. You don't have to go through all the 20 odd pages. You can just go through the first 5 pages so that you're comfortable with, so that you can recall what you studied earlier in linear algebra. Okay. So let me just. So last time we looked at one particular technique, which was subset selection. So remember, when we were doing linear regression, we had a closed form expression for beta hat, right? Beta hat was some arbitrary function. I'm just going to denote the function as h here. Some arbitrary function of your data. So I'm putting again a top bar at the top corner of this x to represent that it's a matrix. It's a matrix which is n times p dimensional. And a vector of your responses. In linear regression we were looking at qualitative output variables, so it was n times 1, let's say. And you can have you can have output variables which are multiple dimensional, but it's not really that different from the single dimensional version of the problem. So it can be n cross k, so you can have k dimensional qualitative outputs, but the nature of linear regression doesn't change. It's almost the same equation. There's really nothing changing in terms of computing the beta hat, only the dimension of beta hat. So in this case, the dimension of beta hat will be p cross 1, and there is a slight issue of intercept, but I'm ignoring that. You can think of one column of X matrix to have all ones that will take care of the intercept. And if Y is k-dimensional output variable, quantitative, then beta hat is going to be beta hat is going to be p times k or k times p, depending on how you look at the matrix. You can always transpose things. It's fine. Okay. So that really did not involve any choice, right? You had the data. There was a fixed function, some product of matrices, inverses, product with a vector, which is this y vector, and you got the beta hat. That's it. So there was no choice involved. And the first method that we looked at where some choice was involved, several choices were involved actually, is subset selection. So subset selection, the choice was size of the subset. I think I use a notation k, but it doesn't matter. So size of the subset was a choice, and the moment you want to make choices, it's not the moment you want to make choice, you want to also do an internal evaluation. That's where we introduce the notion of validation set. Okay, that was one strategy where you kind of break down your training data, the data that you have, n, for example, which have n observations, n realizations of input variables and output variable. You can break that data into two parts and kind of evaluate each subset. Right, that was kind of a proxying for how good your choice is. Each subset choice, and let's say you had if you have p dimensional inputs, then the potential number of choices is 2 to the power p minus 1. Does everybody know why this is the total number of subsets that you could consider? It's a very simple enumeration of all subsets, right? So for example, if there are 3 variables x1, x2 and x3, okay, then all subsets would be x1, x2, x3, x1, x3, x1, x2, and x2, x3, and x1, x2, x3. So we have 7. Okay, just the number of subsets is too many, and so we looked at some shortcut, some greedy way, which was called forward stepwise regression, I guess. I don't know if I use the word, but basically you greedily add one variable at a time, one variable coordinate at a time, and then look at the remaining variables, add one more at a time, and so on. And when you add these guys, you're looking at what the EP, the validation value is. Okay, an estimate of EP is. So that was subset selection. Because we had choices, we had to use that notion of validation. And why are we doing subset selection? Okay, the moment you reduce the number of variables, it should be kind of intuitive that your residual sum of squares, or I mean, I can also use the word in-sample error because your residual sum of squares is a function of your training data, right? So RSS will go up, okay? Because you are using less degrees of freedom. The moment you are using only, let's say, subset of size 2, so let's say P is 10, and you're looking at a subset of size 2, just say x1 and x2 only, whereas here you could have looked at x1 to all the way to x10 to explain, to kind of predict your dependent variable, the output variable. If you're only using 2 instead of 10, here beta is going to be 10 dimensional, here beta is going to be 2 dimensional, right? And so intuitively it should mean that I have less degrees of freedom in terms of fitting a function, like getting a map from input to output, which means that at least the RSS will be higher. Okay, but we don't care about RSS. Residual sum of squares. We care about the validation error, as well as, of course, validation error is a proxy for EPE, which we don't have access to. So, or the test error. Those are the two key things that we care about. Okay, and you will see that by reducing the number of variables, sometimes validation error is better compared to when you don't do success selection. Okay. So that was the reason why we are introducing choice. Why we are not satisfied with just linear regression. Okay, and so in the notes for today's lecture, so this is a table from, I think even lecture 3 may have this table, but I just wanted to show what is the impact of subset selection. So let's just look at the running application from last lecture, which is prostate cancer detection, prediction. So here the response variable was actually a quantitative variable. I don't remember the name. I think it's LPSO or something like that. So we can just look at the first 2 columns here, and let's ignore the last 4 columns. This is just writing out the beta hat coefficients. So if you just do linear regression, you have the closed form expression, just multiply matrices, invert matrices, and so on. You'll get these coefficients. Okay. You can do other things. I think in the last lecture, although I did not go through in the class, in the notes there is a small section about sampling properties of the beta hat or the estimates. It just means assuming some normal distribution is beta hat, you have a hypothesis testing question there. Whether beta hat j is equal to 0 or not, you can do a hypothesis test, and it's related to something called z-scores. So I would say those are somewhat iffy the moment you introduce all these new choices, and you're actually using the training data to do a choice as well as to fit a model. Things are not clear, so that's why I did not go into the detail of these hypothesis tests. But there are a couple of hypothesis tests that are written in the notes from last week, so have a look at it if you're interested. I think these are reported when you do summary of your fit model in R, right? So if you want to interpret that, look at the t-test, study of statistics, and so on. Okay. So here's the beta hat in this case. So there are 9, including the intercept, and the best subset happened to be 2. Okay, so just 2 variables, 2 input coordinates, which were LCA wall and L weight, and with this test error, so the directly reporting test error has slightly decreased. Okay, and standard errors are just so standard errors are basically residuals divided by their variance. Okay. So let's ignore standard error. I mean, it's I didn't define it in the class, but anyway, so test error is the most important thing. It's related to the cross-validation stuff that we did, as well as the choice, right? So we made a choice. We're not reporting residual sum of squares because, of course, the best selection will have higher residual sum of squares, but at least in test, it seems to be lower by 0.03. So this is where the choice, this is where the interpretation comes in. What does 0.03 mean to you? Does it help you, so what is a slightly improved prediction, 5% improvement, or in this case, whatever, 0.03 divided by 0.52, whatever is that number, that percentage improving prediction, what is the impact downstream in the decision making or resolution to a physician and so on. Okay, so that's where we are leaving. We're not discussing that because that's a bit more subjective. But that's the impact of best subset selection procedure. Okay, and it happens for this example that the greedy version of the subset selection, or if you consider all subsets which are 2 to the power 2 to the power 8 minus 1, whatever is the number of variables here, it just happens to be that the best subset size is 2. Okay. Any questions about this part? Yeah.
Reducing the dimensions to get more training error and less testing.
Yeah. I mean, so you don't care about training error, right? You want a function which can, for any given new input, hopefully gives you a number which is close to the true output which you don't have, right? So we have this EPE score, right? For any, so for given a joint distribution between x and y, you're averaging over all x and y realizations this squared loss, right? So you want so that metric kind of is different from just residual sum of squares metric.
What will it impact on bias and variance?
Yeah, so it has so the impact on bias and variance. Yeah, so here again intuitively we will probably look at bias and variance again next lecture. So right now intuitively what's happening is, in terms of you think of bias and variance, last lecture in the first session we were talking about bias and variance. It's important to remember that this bias and variance is for a model, not it's not a single random variable which has or estimate of a random estimate of a parameter of a distribution which has a bias and a variance. So okay, so in terms of intuitively what's happening is you are biasing more when you do subset selection. Okay, so you're increasing bias in the hopes that there is less variance in the model. Less variance in the model subjectively or intuitively just means that it's more stable. Okay, so it's not too sensitive to changing data sets. If you remember in the last class I was trying to say, hypothetically kind of visualize that you had many different n length observations. Okay, so for each n length observation you would have a model, but if you get very different models for each n length data set, then you probably have high variance. Okay, so here by doing subset selection you are somehow biasing your model family or model search, and you're reducing the variance of your model. Okay. But that's just intuitive subjective notion. So we'll again visit bias and variance of models potentially next lecture. Okay. And any confusion, if you're confused, then don't worry about it. We're going to again visit bias and variance a little bit more. It's not central. I mean, it is central topic, but the more central topic is you don't know. What you need to remember is that you don't know what the joint distribution of the data is. Okay, if the joint distribution of data is exactly, for example, 2 Gaussians, right? If data happens to be, for example, 2 Gaussians, I'm looking at the top view, let's say x1 and x2. And let's say you're actually doing classification, it's a different example, but then you know what exactly should be the right model, for example, to classify points from one Gaussian versus the other. Okay, but you don't know the joint distribution, so if you don't care too much about bias and variance, all you're trying to do is ensure that you're not overfitting or underfitting models. Okay, if you have high variance, you may overfit your data. So your model may be complex, so it will be high variant. It will have high variance, but it will have it will overfit. Okay, so it will not do well in test settings. Okay. So when I said, what is the impact of this 0.03 or actually 0.03 improvement in accuracy? Here 0.521 to 0.492. Okay. You need to kind of see. I mean, so what does it mean in terms of that accuracy improvement? So So here the objective was squared loss, right? It's just trying to, since I have a quantitative output variable, we're just asking for how far is my estimate of the dependent variable, I think it's LPSA, compared to the true dependent variable measurement, right? But you can imagine a classification problem where you're saying whether cancer exists or not, okay? Then you can ask whether you're falsely predicting whether there was a cancer when there was no cancer, or when you're not predicting cancer although there was a cancer. Okay, it's then you can, in that setting, think about what is called sensitivity and specificity. So we'll get to those measures later. So these kinds of decisions kind of impact your model fitting exercise as well. So in the regression, there is really nothing. What does this improved number mean? You're making a better prediction. Okay. What does better prediction impact in terms of a downstream task? It depends on the task. In this task, if it's going to be a decision aid, maybe a doctor would like to know, plus or minus whatever 0.52, you may, you're predicting the measurement without doing the measurement of LPSA, for example. That is the dependent variable there. Okay. So let's look at another application. It's called salary. So this is just a straightforward application, but I thought I'll include it just to motivate, a very recent example. So this is by some folks at Stack Overflow. So how many of you have not heard of Stack Overflow? Okay, Stack Overflow, for those of you who have really not heard about it and don't want to say it here, is an online question answering site. So they have, so basically they provide a community where people can ask questions and hopefully some experts will answer and you kind of clear questions, and it's also very useful for in your own programming tasks, especially Stack Overflow. But it also has a job board. Okay, so what these guys, and actually I guess that's one of their business models, to have a job board and get money. The people who want to post jobs will pay them money, and so they really want a good visit count on the website. So anyway, so they created this informational tool for both job seekers and employers to know what is the kind of average salary for a certain type of employee. Okay, so what they did is they actually didn't have any data. I guess they didn't have any data, and then they actually surveyed people about what is their qualification, what is their experience level, what are the technologies that they use, and so on. And they created they sent out a survey, got entries filled by various people of different with different salaries, different education levels, different experiences, and so on. So that would be your N of your X matrix. Okay. And then they did, so the first step always should be some exploratory analysis. So here is some exploratory analysis in an interesting graph here. Here they have one of the independent variables to be years of professional coding experience. So this is specifically for developers, but because I guess their audience are developers, and they're showing median salary in US dollars, I guess, and there are different countries. So they ask the location of the respondent who's filling the survey, and here you can see there's some positive relationship between more experience and higher pay, and maybe plateaus after some time. So this is just an exploratory plot. You can they plotted. Okay. They also had an interesting problem where in the survey they were only asking about the location, which was the country. Okay, but they also wanted to, but in the US, for example, they observed that the salaries paid to people in certain economic regions, San Francisco and New York City, are way higher than the rest of the country's average. So they wanted to kind of figure out location by city as well. So they used the IP addresses which they log of people responding. They did some geolocation of the IP addresses and got the location of the cities as well. There's another plot, I think in figure 3, where on the x-axis is a median salary and on y-axis is the different I guess types of developers, different categories. Okay. So these are just summary statistics of their survey. Okay. 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 So another so they did this exploratory analysis. The couple of key things that you might want to observe, which you did not see in the lecture. The first thing is some of these independent variables or the input variables are categorical. Okay. So did you guys have to deal with categorical variables in the first assignment? Okay. Okay. So if you have categorical input variable, you'll have to do something clever, right? I mean, how do you encode? So this is a categorical variable which has different values. How are you going to encode it as a coordinate of your input? Let's say you want to do linear regression, right? It's not clear. So does anybody have an idea of how to encode categorical variables? Yeah. So the answer, as some of you have pointed out, is to use indicator variables or dummy variables to represent this particular single categorical variable. So if you have so I'm just going to write two twists in this story. The first one is they have a categorical variable. A categorical variable. Location is also a categorical variable. So you want to convert this into a set of okay, I don't want to say. So you basically, instead of one coordinate, you basically translate it into several coordinates. Okay, so that's one twist. And the second twist is while doing exploratory analysis, they felt that the response variable y, it's better to model it as it's better to transform it into log of y value. Okay, because they felt that y is log normal rather than normal. So okay, so we'll actually get to this charts again potentially in the next couple of lectures. But in linear regression, if you remember, we were thinking of y as x transpose beta plus epsilon. I mean, to talk about properties of linear regression or some kind of intuition behind linear regression, we were talking about y is equal to x transpose beta plus epsilon, right? But epsilon, for example, was normally distributed. Normal just means Gaussian. Okay. So they felt that instead of y, whatever is the raw observations of the dependent variable they collected, they took the log of y as the dependent variable. Okay. So this is just a transformation, right? For the input variables in one of the either the previous lecture or the lecture before that, we know that we can always have interaction terms or transformations of the input variables. So if I have xj, I can always think of xj square, xj cube, and stuff like that, right? If I have an independent variable which is quantitative, I can just square it or take a log of it and so on. These are all explorations that you can do. So these are all choices. Now the moment you introduce choices, you can always go back to validation, cross-validation, and that's all you need to do. Okay. Yeah, so this is the second change, and given these two changes, they just did linear regression. So no ridge regression or LASSO that we're going to see today. They just did linear regression, and they have a tool which is live online. I think this whole regression analysis, this tool was set up on 19th earlier this week. So some data science people in Stack Overflow organization set it up. So you can look at the tool, as well as I think I have given a link to a discussion page where the users are now telling whether they find it useful or what improvements can be made. Okay, so that's the whole life cycle of getting data, doing exploratory analysis, using some model. In this case, they fix a model to be just linear regression, and once you fit the model, then you kind of create a tool, which I guess requires setting up a web server or some kind of a API service, which kind of takes inputs in for any new person coming to a certain web URL and outputs some nice results about what is your salary, median salary, and stuff like that. And they also have the closed loop where some people are able to give feedback about the tool, and that's because it is a discussion forum. Yeah. Okay. Any questions about this full life cycle of analytics project? Okay. I don't know why the battery indicator is always showing. Okay, so today we're going to look at slight variations of subset selection. So which are going to be ridge regression and LASSO. So first I'll talk about ridge regression. I guess the first question that comes to mind is, what's the shortcoming? What's the shortcoming of subset selection that, which kind of warrants a couple of other methods, right? So subset selection is actually discarding full coordinates, right? So if you had a location coordinate, for example, in the previous example, then you're completely discarding a location coordinate. So that may be kind of, you collected all the data, maybe some measurements of certain coordinates of the input variable are pretty expensive. So you want to actually not do, really remove them. You want a method which kind of softly removes them, in the sense the beta coefficients that you can have, we are in the linear model land. Hopefully the beta coefficients are small, so that even, collected the measurements, the beta coefficients can be small, so that the effect of that particular input variable is not there on the dependent variable. So it's not being used for prediction. So you want a softer version of subset selection. Okay. Subset selection is a hard version, because hard and soft just means that I'm actually just deleting columns of my X matrix, right? Instead of deleting the columns, you keep the columns, but you kind of hope that your method produces a linear model coefficient vector, that beta hat, where the coefficients are small if those columns are really irrelevant. Okay. So ridge regression is actually quite easy to understand. So I guess ridge just comes from signal processing or geophysics communities, I think. So what does it actually mean? So we just modify the definition of RSS, so residual sum of squares, where we now introduce another parameter lambda, okay, and we already have beta, and I'm gonna write it in vector notation, okay. So y minus x beta transpose y minus x beta. Okay, so that was the original residual sum of squares. I'm going to add a penalty. Okay, I'm going to call this a penalty, which is below. It's going to be lambda times beta transpose beta. Okay. So instead of trying to score any model, so model is just the one corresponding to the appropriate beta. For every beta there's a model, right? So instead of scoring models just based on residual sum of squares, I'm going to score models based on a slightly different objective that I have an additive term. And the additive term doesn't depend on data, and so I'm just going to call it a penalty. Okay? And generally lambda is going to be positive. Okay? So it's a choice. I mean, it's a choice in the sense it's another parameter that you may want to choose. Okay. So what happens when lambda is equal to 0? just a consistency check. Huh? Yeah. So when lambda is equal to 0, it's just linear regression. I guess, I don't know if they call it vanilla linear regression, but anyway, linear regression without bells and whistles. And so what happens when lambda is equal to 1,000? Okay, what do you think intuitively would happen when lambda is set to be 1,000? So I fix lambda to be 1,000, and now I'm saying I'm squaring every model based on this objective, yeah. So what happens when lambda is 10 to the power 9? Huh? So lambda equals 0, we just said it's going to give us beta hat, the vanilla linear regression, I don't know what to call it, but there is no beta hat. When lambda is equal to 1,000, it will give me some other beta hat, right? Some other beta hat would be one of the one model would be the model which has the lowest RSS lambda comma beta, right? And here I'll get some other beta hat as well. So there are 3 different beta hats for each of the lambda values. I guess what I want to drive at in terms of intuition is that when you increase lambda really large, you will see that beta hat j is almost going to be 0 for all j is equal to 1 to p. Whatever is the p, beta hat is p-dimensional. So all I'm saying is when you crank up lambda to almost unrealistic value or something like that, you will see that betas are going to be 0. Why is that? Because the larger the magnitudes of betas, so beta transpose with beta, beta transpose beta is nothing but sum of beta j squares. J is equal to 1 to p. This is just the inner product of 2 vectors. Inner product of 2 vectors with both vectors are same is just the sum of the squares of the individual coordinates. So it's a number which is greater than 0. So you can see that if I have betas non-zero, okay, so this square this will have a positive value, and I want to minimize. So whenever I'm searching for a beta that minimizes, for example, this modified RSS, and then I'm preferring betas which have low values, right? Because the moment betas are non-zero, I have a term here, so that is less preferable to a beta which has zeros. Okay, is that clear? Is this intuition at this point? We'll actually more carefully reason about this very soon. So the reason I've introduced age regression, there's another quick intuitive reason that I want to give, which is as follows. Let's say y is equal to x1, some beta x1 plus epsilon. So there's only one, p is 1 here. Okay. So let's say I made I have one input variable. Okay, just one input variable. This is just one dimensional. Okay. Let's say I have made a copy of that, which is basically x2 is equal to x1. Okay. Now I introduce that, and so I want to find beta 1 x1 plus beta 2 x2 plus epsilon. Okay. So when I introduce another measurement, let's say it's exactly the same as the first measurement, then I have basically 2-dimensional input variable, and I have, let's say, 1-dimensional output variable. So basically I have a different linear regression problem where I'm searching for 2 coefficients, right? I mean, there's nothing changing here. So you can see that these coefficients can be, let's say this beta is actually, let's say it's exactly equal to 1 times. So let's say the real data actually is y is equal to x, okay, on average. Okay, you can think of epsilon to be 0 mean a normally distributed random variable. You can imagine setting different values of beta 1 beta 2 and still getting the same effect. For example, if I choose beta 1 is equal to 3 and beta 2 is equal to 2, I get the same, actually not 2 but minus 2, let's say. Then 3 times x1 minus 2 times x2, which is also x1, is just 1 times x1, right? So this is also a feasible, this is also a model which will get the same RSS as considering the RSS in this model, right? Intuitively, these are all, we're not talking about exact specific things here, but intuitively you can imagine that if I'm doing a one-dimensional regression with just one coordinate as input variable, maybe I'll get a beta hat which is close to 1. If I'm doing a two-dimensional regression, okay, and x2 happens to be x1 exactly, and if this is a true model, then maybe I'll get a beta 1 beta 2 such that the difference is almost close to 1 or exactly 1, okay. So you want to avoid these situations, and that's why this is another reason why you want to penalize large values of beta or beta j. Okay, j is equal to 1 to p, and that one version of penalty is this one. Okay, you want to keep the coefficients small. For any fixed lambda, it's kind of affecting. It's trying to make the coefficients closer and closer to 0. Okay, that's just an intuition again for why we added a penalty. Okay, and it's a second intuition because first one I said was we just want a softer version of subset selection. We don't want to just delete input variable, coordinates of input variable. We just want to, we just want to do it softly. So that's why we added a penalty. Yeah.
I want to understand, why you say we don't want that situation where we have 3 and 2 by minus 2?
You're estimating more numbers, right? Estimating more numbers from the same data is tougher in the sense you will not get good estimates compared to estimating less numbers intuitively, right? So let's say I have 10 observations from which I want to estimate 5 numbers compared to 1 number. Estimating, using all the data to estimate 1 number is kind of easier, a better statistical setting compared to estimating more numbers. In a sense of, this will be high variance. This will be a high variance model. So this is called the collinearity problem, and I don't know if you've done 570 SOC, you might have kind of come across the term collinearity, right? So this is related to that. And in general, you can imagine if you have input variables, they can be very strongly correlated with each other, and then that may mess up. I don't know if you've done any experiments, but that will mess up your estimation of coefficients, and it's subjectively a bad setting to have very highly correlated input variables. Okay, and we'll see. Actually, today we'll see a fix for dealing with this correlated variables issue as well. Okay.
But could we say that we are trying to stabilize our beta because instead of 2 variables which are kind of similar,
Yeah. Subjectively stabilizing may mean something. So there may be, I don't want to use the word stable without defining it. And again, whenever I say something, either it's mathematically, it makes sense, or subjectively there's some intuition-driven reasoning. And what you said is an intuition-driven reasoning. It seems fine. Yeah. I don't want to say, there may be actually, since I'm not a walking encyclopedia of statistics, maybe stability is used elsewhere. I definitely know one place where in statistics stability is used. I don't know what the context is, so I don't want to use the same word. Yeah. Yeah, but the intuition is correct. Basically, when you have collinearity, you will get things which are, unstable in a way. Okay. Oh, okay. I missed a plot from the salary calculator example, which I wanted to show, just to kind of say that they chose linear regression, and they're plotting residuals. Okay, instead of plotting residuals, all the residuals, they're just plotting residuals per location. Okay, so they're just seeing condition on each location, condition on each of your categorical variables, which was transformed into these dummy variables being true. How does the residuals look like? And it's just I guess a subjective interpretation of whether linear regression is working or not. So for example, for the United States, you see some ideally want residuals to be like a band. So you see that is not the case here at higher and lower values of these log salaries. Okay, so maybe linear regression is a good model. If you don't have a good spread of residuals, maybe linear regression is not a good enough model. Okay. So here are some post model fitting diagnostics that you can also kind of see. Okay. Sorry about that. Okay, and we'll just eyeball the solution for ridge regression. It's pretty easy, and it's as follows. So remember, so what is RSS of lambda beta? I'm just now going to expand the squares. Okay, I wrote a vector transpose vector as the expression before, right? So let me just expand the squares. So what is the expression? So it's just y vector transpose y vector minus y vector transpose x beta, x vector beta, sorry, x matrix beta, minus beta transpose x matrix transpose y vector, and then plus beta transpose x matrix transpose x matrix beta. So this you have seen like 2-3 times already. It's just an expansion of the squares for the first term, and then we have the second term, which was plus I'm going to write it as beta transpose lambda times identity beta. Okay. So this so just a side note that when you write lambda beta transpose beta, I just rewrote it as beta transpose lambda times identity times beta. This is nothing. So these are both scalar values. Okay. What is identity? Identity is a P cross P matrix. Beta is beta transpose is a 1 cross P matrix vector, and this is a P cross 1 vector. Okay. Nothing changes here. If you just evaluate this term, it's just same as beta transpose beta. Okay. Right, I just expanded the definition of RSS with the lambda there, and you can just see that this is nothing but all these terms are the same. Right, let me just call this same, and then I can add this beta transpose x transpose x plus lambda times identity beta. So the only term that changes is the quadratic term, right? And so, by visual inspection, you can claim that beta hat is nothing but x matrix transpose x matrix plus lambda times identity inverse x matrix transpose y. Okay. So there is a closed form expression for the ridge regression coefficients if given a lambda value. So do you guys know what is meant by singular matrix? So when is a matrix A called singular? When what? Determinant is 0. So if matrix A is singular, then you cannot define A inverse, right? But if you add a matrix A with identity, okay, does it remain singular or not? Huh? It will not remain singular, or it will remain singular? Okay, yeah, it will not remain singular because identity, so for those of you who don't remember, identity is just ones in the diagonals and zeros elsewhere. Okay, this is a matrix. Okay, zeros are all over the place except for the diagonals. Diagonals are ones. So the rank of this matrix is whatever it is. Like if it's a P cross P matrix, it's P. Okay. And so if you add an identity to another matrix, since it's full rank kind of ensures that the matrix is not singular. The resultant matrix is not singular. So its inverse exists. So here, for regression, this additional additive term is ensuring that the inverse exists. Okay. This helps in situations when you have less data. For example, if you have less data than the dimensions, then X transpose X is going to be not a full rank matrix. Okay, you can verify that in your homework. So, okay, I guess what I'm saying is, if n is less than p, then X transpose X matrix, the matrix times matrix, is not full rank. So X transpose X, by the way, is p times p. Okay. So this, we can explain it, but it's just a quick thing you can check. Okay, so let's just quickly look at a plot. This is figure 5 for the same data set, the prostate cancer data set, and they're plotting. So what they're doing is they're picking every different value of lambda. Okay, so lambda is a choice that you could make. So they're just asking, okay, for different values of lambda, what's going to be my beta vector? Okay, the beta hat vector. And interestingly, they don't want to plot with respect to lambda. They want to plot it as a function of lambda. So here they have df of lambda. It's actually just inversely related to lambda in the sense that when lambda is large, df of lambda is very small. Okay, think of it as like 1 by lambda. So when lambda is large, 1 by lambda is very small. Okay, for example, if lambda is 10 to the power 9, 1 by lambda is 10 to the power minus 9, which is very close to 0, right? So for very small values of lambda, they get some coefficients here, and they just plotted the coefficients. So all the coefficients are plotted as at the same point, okay, at the same x-axis, and they're just saying, okay, I can keep on increasing lambda. If you remember, we said that if you increase lambda, then the coefficients have to go to 0, like kind of get compressed in some sense, and you can see that they in fact have that when lambda is really large. They have all coefficients tending to 0. Okay, so that's the effect of the Ridge penalty. Okay, which may be useful or not. But now the choice of lambda. How do you pick choice of lambda? It's very similar to the choice of subset size that you're doing for subset selection. So for each subset size, let's think of a simple strategy, not the cross-validation strategy. You had the training data, you left out a part of your training data as validation data. So every time you make a choice, you can just evaluate how it's doing in terms of, let's say, squared error or whatever is the loss on the validation data. So for every choice of lambda, you can do the same here. Okay, just like you're doing for every choice of variables, you're just asking what is the validation error, right? And you can pick, I think, the vertical line, vertical dotted red line here, which is very faint there. They're choosing some appropriate level of lambda. Okay, because every lambda will influence what is the final beta hat that you're gonna give to your manager as is the final output for you. Okay, so let's just choose this lambda for this regression, for this data set. Okay. There is an interpretation of I think when we're doing just linear regression in linear regression we related residual sum of squares to some maximum likelihood estimation problem. Remember maximum likelihood estimation? In fact, we said it's a maximum likelihood estimation problem where, for example, a model where y is equal to beta transpose x plus epsilon, where epsilon is normally distributed with some mean 0 and variance sigma square. Okay. For this model of observations, this model of dependent variable given x. Okay. If this is a model, then the maximum likelihood estimate of beta hat is the same as RSS. There is probably some coefficients. In a sense, you get the same beta hat. So if you do maximum likelihood estimation, then when you write down the likelihood function and take the log of it, it just looks like C squares objective. Okay. So I don't want to write it again. So in linear regression we did that, and even for ridge regression we can do the same. We are putting same in quotes because now you want to talk about what is called maximum a posteriori estimation. Okay. So these are just acronyms. I've expanded the acronym in a more, but so it's not very different from maximum likelihood estimation. So what is MAP? For that, let's just kind of remember Bayes rule. So how many of you have not seen Bayes rule before? Okay. So how many of you have not seen the definition of conditional expectation? Conditional distribution. Okay. So let's see. So if you remember probability of, let's say, two events, right? P of A given B is just the P of B given A times probability of A divided by probability of B. This is just definition of conditional distribution, I guess. Condition, yeah. So Bayes rule is very similar. So you just substitute A to be a parameter and B to be your data. Let's just use the word data there. So probability of parameter. So now your parameter is actually think of it as a random variable. Okay. So here I'm talking about events, but you can write the same thing for random variables. Okay. Probability of theta given data. Let's use capital. Is equal to probability of data given theta times probability of theta divided by okay. So if you remember from a couple of lectures, this term probability of data given theta was the likelihood. We just we call it likelihood. There is nothing else going on. This is called a prior. Okay, that's how it relates to Bayes rule. So in this expression, you can think of it as a Bayes rule, where you can think of this as a prior, this as a posterior. Okay, these are just words used to describe the terms in this expression, and this term is called the likelihood. Okay, so this is called posterior. It's just a naming of different terms in this expression. There is nothing going on. So why did I bring this up? Because maximum likelihood estimation is just trying to do this, which is maximize over theta, which are parameters of probability of data given theta. Okay. is just trying to maximize the likelihood term. If you want to maximize something else, in this case, you want to maximize not the, so on the right hand side, if you see the denominator term is not a function of theta, so you can kind of ignore it, because even if you change different thetas, the denominator has no impact, has no impact. Its value won't change, whatever value it evaluates to, right? So let's say you want to maximize over theta of p of given theta times p of theta. Then this is called the map estimation problem, MAP problem, and this is called the MLE problem. Okay, and we saw that this term here, if you take the log of it, was the residual sum of squares for a particular data model. Okay, 2 lectures ago we said residual sum of squares is the same as MLE for a particular assumption about how y is related to x. Okay, so the reason I brought this up is because ridge regression can be thought of as MAP, where it's the same assumptions as before for the likelihood part, but the trial part is gonna assume some distributional assumption on beta. Okay, make some appropriate distributional assumption on beta. In particular, that beta is also normally distributed, and then you'll get this penalty. If you take a log of product of 2 Gaussians, you'll get 2 square terms. One of the terms will not be a function of data at all, and that will be your lambda times beta transpose beta. Yeah.
So when you are estimating the maximum number of beta, we can go to tell that beta 2 should not be equal to 0. Then we can reduce the training error.
No, can you repeat your question?
So here we are estimating the maximum number of beta we can get, so that beta cannot be equivalent to 0, and at the end we can reduce it as well.
There are 3 statements there. So you're talking about what I wrote here, or you're just talking about ridge regression?
We replace that beta with beta.
Yeah, so in fact, yeah, that's what we do, sure. So you're talking about MLE problem, or you're talking about the MAP problem? Because MLE problem, we already related it to linear regression. Yeah. So you're talking about MLE. So MAP, there is this second term which is called the prior term on beta. All I'm saying is you make an appropriate distribution assumption such that if you take the log of this, if you take a log of a product of 2 terms, log of A times B is log of A plus log of B. If you remember, for linear regression, we made the first term normally distributed. If you make the second term also normally distributed, I just use the n term to represent normally distributed assumption. Then if you take the log, you'll have 2 terms. The first term will be just the same as RSS term, which was the sum of the squares of the difference between yi minus xi transpose beta. The second term, if you make a normal assumption, then it will also look like beta transpose beta. Okay, it just happens to be the case. There's nothing else going on in terms of test error or anything else that you said. Is that clear? Okay. Any other question? Okay, let's take a break for 10 minutes and then we can resume. What we are trying to do is, what I was asking is, can you replace this theta with beta? Yes. So that previously we were trying to reduce this number of beta, so that the final beta should not be equivalent to 0. Yeah, we are trying to reduce the number of non-zero betas in such a circle. Yeah. So here we are, by where we can maximize this number of betas, we can put in the model. We are not maximizing the number of betas. So if you want, I can write the exact expression for this is a recall. I guess recall this recall. Let's assume a particular model y is equal to x transpose beta transpose x plus epsilon. I'm going to say epsilon is normally distributed with mean 0 and scalar epsilon. This is the only random variable. Then you can see that y, probability of y is equal to little y for any value of y is just 1 by square root 2 pi sigma e to the power minus 1 by 2 sigma square of okay, let me actually write y given x is equal to x, little x, x transfer is beta minus y. This is definition of normal distribution. Okay, yeah. So this is actually equal to, I mean, your probability of data given theta is nothing but, it happens to be if you have n data, n observations, then it's just a product directly represented as a pi. It's just, okay, let me actually write it. P of y is equal to y1 given x is equal to x1 minus P of y is equal to y2 given x is equal to x2 and so on, and that just happens to be equal to and if you take the log of the left hand side, log of this thing here, then it will be sum over I is equal to 1 to n of log of P of y is equal to yi given x is equal to xi, and it's just product of bunch of terms, log, taking a log is the addition of terms, and I just told you what this is. So if you take the log, it just is proportional to sum over I is equal to 1 to n. If you take the log of the exponent of something, right? Okay, log of x exponent, yeah, you can ignore these real constants, and there will be another coefficient here, but it basically becomes xi transpose theta minus yi square, and this is actually equal to RSS of theta. So that is that part, and the second part you can assume a normal distribution on beta as well. So that's the, I'm not doing that here because it's actually probably a silent question.
We add the lambda part. So after we get the RSS theta, we add the lambda part.
So you need to have this addition product, addition term there. Probability of beta, you just assume to be normally distributed, and it's basically the same computation. You just see that it's RSS lambda theta, lambda beta actually. It will be in the thing.
And somewhere the assignment of 11:15
Did you send me an email?
No.
Yeah, it should be fine. I think the PS will look at the time submission.
It showed late in the...
That's okay. I think it's just a software thing problem. Don't worry about it.
One thing is about submission. So whatever I did, I submitted in the markdown file, but then I converted markdown as a PDF using PDMTR, and then I submitted on the PDF file. So it included code as well as output. So I thought that would be sufficient.
That's fine. Okay. So you send me an email, right? So you don't have to do it. Will you not send me an email? Who send me an email? Somebody did the same thing as you.
Okay, just PDF?
I think so. PDF, I think they also sent the code, but they did not. Yeah, they were mentioning that they did this.
Yeah, because I thought whatever the whole point of zip file was, you wanted to look at output as well as code. But in PDF, you can see what's in it.
Yeah, sure. Thanks.
That is
Just a quick question on this. I used the same thing, but the point was like I had some problem with Metrics because it was giving me the link for basic installation, and when I was running it, I was converting my file into PDF. It was saying that I have to have a complete installation, then basic installation. So instead of converting into PDF, I saved it into Word file and then converted it. Is it fine?
Should be fine. So why don't you make it as HTML? Is there no export for HTML?
No, there were three options. One was for HTML, one was for creative.
Next time you're testing, you should just make it HTML and then just print the file or something and just make it a PDF. It's just easier. I mean, so okay, you made it a Word, but submit the Word or the PDF version?
PDF.
Okay, that's fine.
I've also submitted the R&D file.
Okay, that's fine.
And regarding final exams, actually I am planning to graduate this one. So on 16th, according to this conventional schedule, there is the ceremonies from 9 to 1. So that is why I wanted to ask you, can you send me an email? I need to check with the department. Yeah, this is here is the website, UIC commencement, and so event details December 16. Graduate is from 9 to somewhere it will end at 1 or 1.
Sure. Yeah. Send me an email with this link.
Yeah, sure.
Because this is, I don't want to set it on 16th. It's just, they have told me that it should be on 16th. Right, the same UIC.
And in previous classes we had seen similar conditions, so professor kind of tend to accommodate and they're little flexible on the calculation rates.
Okay. But send me an email. I just want to check with the department.
So will it be on the same day, or can we do it the day before, or will we be able to take it?
We will see. Yeah, just send me an email. I'll resolve the issue.
I have a symptom that I'll go to my ticket on 16th December in India.
Okay.
For some family function. So don't have the same problem.
Did you book it after we told you?
No, I did it before.
No, but I told you that the tentative exam schedule is not announced.
I booked it before.
Send me an email. I don't know what I can do, but we will see. I mean, sir, it's not completely in my hand actually. I need to check with the department because I don't want to take arbitrary decisions and set up policy, right? So there's probably a policy in the department. I just thought about. I'll check. Send me an email.
So the interaction question that I had asked you earlier. So I mean, is it more of like when we have to choose at all? Let's say we have to take all of it and
You will see that the regression receivers may not be like spread out or something, then we'll probably have to introduce instruction terms.
yeah. Okay, I mean that's why when we basically introduce interaction test for the first time. And let's say if we have to choose whether we should choose this one or this not.
Yeah, it's not clear.
It's not clear,
The
right?
thing is infinite choices, right?
That's
all
right,
the
exactly.
things. That's right. So this is the issue of data science. Right? You don't want to exam distribution. If you know exam distribution, you can exactly compute the distance boundary, that is classification, or you can exactly find the expectation of y given x, and be done with it. The whole reason, because we don't know anything about the exam distribution, we are doing all these things.
So I mean, let's say if we take let's say 2 or 3 times, 2 or 3 interaction times. So I was calculating the regression model. I mean, I was evaluating the regression model again. And sometimes those 2 terms were coming, when the model is significant on the basis of the statistical value. Values, and sometimes they are not.
That's right. So things may drop out or become significant depending on which other terms are there in the
That I understand.
So that is an issue.
So let's say at the end we have like 2-3 models, and then let's say we decide our interaction terms. And then we have to decide. Then again, is it the solution like we have to go for cross-validation and check the actual test error whether it's making?
The choice of interaction terms also you can do cross-validation. And later on maybe we'll see ensembling where you don't want to make a choice and just take all the predictions from the average or something like that. There are all these tricks, but we are trying to kind of circumvent the issue of this choice.
Because when we talk about cross-validation, I mean, it becomes a tedious job, I'll say, even if it's it's tedious, right? I mean, because we have to do 3 times.
I didn't say the assignment of last month was time, but
That's fine.
I saved it with my UIL.
So fine, that's fine.
So that state cancer example, you said that if it's a categorical variable, we will create it into dummy variables, 1, 0, right? That's what I understand. Can we kind of take a factor of it and do it? Factors, as in we can just convert it into factors and then...
In our language, we are language independent, but all it's, I think when it does factors, it's probably doing the same as what we say.
Right, we can do that. And secondly, you said that we take a log transformation. So we
They did long transformation for starter flow, but we will see these transformations. For the dependent variable, there is a specific name. We are generalizing them out, we will see them later.
So they did it on salary variable or the... So I was thinking that why do we make a log transformation to 1, 0? So that doesn't make sense, right?
Yeah, so it's fine.
Just want to say thank you for the help. Number one.
Okay.
Right here in the back of the
No problem. definitely use lat because it's an ion feature and
I use that too.
I saw that.
Yeah, that's actually helped me out because the guy say, hey, I tested, it'll work. You listen this and this and that. And it worked in the end.
Good that you got to the
Do we have left today?
I think so. Hasan is gonna say something. Yeah,
All right, thank you very much.
Okay, so we'll resume. Okay, so let's actually, let's spend some more time on regression, although it seems like a trivial or a very straightforward extension. But this time we're going to introduce another tool while interpreting the coefficients of ridge regression. Okay, and the tool is going to be singular value decomposition. Okay, so we're going to look at ridge regression again from the point of view of singular value decomposition. How many of you have not heard of singular value decomposition? How many of you have heard of singular value decomposition? It's okay, I mean, not heard. So who has heard about SVD? You have? What do you remember about it? Oh, you took it in a linear algebra course? Okay.
The number of observations are verified within
So your thoughts are, if we have number of observations which are large, then we should go with SVD for some reason. Okay. Any other thoughts of why SVD may be important or why did you go through SVD in your previous courses? Okay. So in this exercise we're gonna try to understand again, what is ridge regression doing in terms of SVD, okay? And we already have said intuitively what ridge regression is doing, which is to scale the sum of the coefficients to 0, right? In fact, scale all the coefficients some way, but what is the impact of that scaling on different coefficients? Hopefully it can scale down the coefficients of those variables which are kind of irrelevant for your prediction, right? So it's a soft version of subset selection. So let's look at that. So SVD view, okay. So what is SVD first of all? So SVD, just think of it as is a factorization of a matrix. So if you have a matrix X, okay, I can break it down into three matrices: U, B, and V transpose. Okay. It's just if you have a matrix, how many different ways can you get different matrices whose product somehow happens to be the same matrix. Okay. SVD admits a particular form. It's a product of three matrices. I don't know if you've done a linear algebra course, you might see other matrix factorizations like QR decomposition and so on. It's just some nice families of creating products of matrices which will give you the same matrix. Okay, so in this case, X is the input. Given X, I'm creating a U, I'm creating a D, and I'm creating a V matrix such that the product in this way is going to give me an X. Okay. So what is so it happens that U is orthogonal, D is diagonal, and V is also orthogonal. Okay. Orthogonal. Okay, let me say what orthogonal means. So let's if U is a matrix. Okay, before we get into orthogonality, what is the dimension of U? So let's say X is n times P. Okay. Then U is going to be we can take U to be n times P. Okay. D is B to be P times P, and V to be P times P. Okay. So I'm just trying to match the dimensionalities of these matrices. Okay. So let's say U is n times P. I can write the U matrix to be U1, this is a column, U2, this is a column, and UP is also a column, right? I can just stack the columns next to each other, and I get and each column, basically U1, U2, UP are n dimensional, and you get an n times p matrix, right? Okay, so what does orthogonal just mean? Orthogonal just means that UI transpose Uj is 0. Okay. So matrix is orthogonal if its columns are perpendicular to each other. Okay. And when we say columns are perpendicular to each other, we just mean that the inner product with I not equal to j, with other columns, it just happens to be 0. Okay? It's just a special property that these matrices have. And for any matrix, we can create an SVD decomposition of that matrix, and where the SVD matrices, like the U matrix, has this property that UI transpose Uj is equal to 0. D happens to be a diagonal matrix, so it's just all zeros everywhere else. On the diagonals, there is non-zero numbers. Okay. So why did I need this expansion? Is because when you look at the closed form expression for beta hat, it had a bunch of matrix inverses and products, right? X transpose X inverse plus lambda I, X transpose X plus lambda I, the whole inverse times X times Y, something like that. So let's look at how does this look like. So this is going to be X times beta hat. How does this vector look like? So what is this vector? Beta hat is always p times, in our narrative it was p times 1, and X is n times p, right? So this is actually our prediction, maybe I should beta hat. This is our prediction vector, okay, on the training data set itself. Okay, so it's like on the training data set itself, and it is actually equal to just X times X transpose X plus lambda I inverse X transpose Y. Okay, that's just the definition of the beta. Okay. And now the reason why we introduced the SVD tool is to just reason about what's happening with the reason about what's happening when we introduce this lambda term. Okay, and we'll say how does lambda term influence something? It is influencing something, right? It's somehow shrinking the coefficients of beta. That's the intuitive explanation. But so what we're going to do here is just substitute X with U V transpose. Okay. Substitute the X matrix with this decomposition, and since U is orthogonal and V is orthogonal, I think U transpose U is identity. So orthogonal matrices satisfy this property. Okay, you just if each column vector is transpose times other column vectors is 0, then this just happens. Okay, I just stack those results together. If you use this, you just substitute X with this and use this property. Actually, even V is also orthogonal, so you will have V transpose V is equal to identity. Okay, then you will see that these predictions X times beta hat is actually equal to sum over j is equal to 1 to p of uj times dj square divided by dj square plus lambda. I'll tell you what dj is. Uj transpose 1. Okay. So this, you can just substitute and cancel a lot of things. I don't want to do it here. like because of all the products and the inverses and so on, ultimately what you'll see is that the right hand side, the extrememost right hand side vector still remains the same. It's y, right? The things which cancel with each other are u transpose u and v transpose v, things like that. And these, I didn't explain it before, but B matrix is actually D1, D2 on the diagonals to D P. Okay, it's a P cross B matrix. I think I said that before. And zeros elsewhere. Okay, whatever up and down. Okay. So why did I do it? So I just said, okay, let me just do an SVD of X. I substitute the definition of SVD, maybe there's some U, maybe there's going to be a V and there's going to be U matrix. I just substituted that and I got this reduced form, okay. From here I want to interpret what's happening, okay. So what is Uj? Uj, if you remember from just above, it was just the jth column of U. Okay. See this U1 is the first column of U, capital U2 is the second column of U, right? And Uj is the jth column of U. Okay. How many columns are there? There's going to be P columns. P such vectors next to each other is define U. Okay. So if you look at this, and I said this is, I think I used the notation I had. These are the predictions on my training data. Okay, that's the vector which is n times one dimensional. Okay. So you can look at this as let me rewrite this. Again same thing. J is equal to 1 to P Uj times dj square by dj square plus lambda times Uj transpose y. Okay, that's what this. I just rewrote the same thing. Now Uj transpose y, as I said, U is actually n cross 1 dimensional. It's a column of the U matrix, right? So Uj transpose y is actually a scalar in the sense that it's this number. This is just a number, right? Dj is just one entry of the diagonal matrix. Okay. So this is also scalar. So all we're doing is some sort of a linear combination of, it's basically some alpha I times ui. Okay. So ui is, remember, is n times 1. Okay. It's a column of the U matrix. And so all I'm saying is my predictions are just going to be some linear combination of all these columns of the U matrix. It just happens to be the U matrix from the SVD of X. Okay. So I had X, I did the SVD, I got the U matrix. I have a bunch of columns of the U matrix. I'm saying some combination of, add and subtract these columns, that will give me my prediction y hat. Right? Because this is scalar, I'm just adding a bunch of, rescaling multiplying the columns of U matrix with some numbers, these two scalars, and I'm just adding them, and that's going to give me my prediction. Right? So what so now let's think about what lambda is doing. So lambda, it's actually, first of all, let's focus on the scalar. Do you agree that dj square by dj square plus lambda is less than or equal to 1? Why do you think it's less than 1? Yeah, lambda is positive, and dj square is positive. So just dividing a larger number with a smaller number. So it's less than 1. And when lambda is equal to 0, the dj's are, so what happens is this ratio. It's just 1, right? So if you think of the scalar, that's the only space where lambda is appearing in terms of predicting your training data y hats. Okay. And when you set lambda is equal to 0, you are in the linear regression version of the problem, right? And linear regression, so in fact you can just write this as the linear regression version, the linear regression solution looks like this, where you do the SVD of the X matrix and get the U's. So you can write this, you can interpret this as an alternate representation for the predictions for linear regression itself, right? When I set lambda equals 0, this is the formula for predictions on your training data, okay? And when I introduce lambda, non-zero, all it's doing is changing the scalar, okay? Every scalar, every alpha, so this scalar times scalar times scalar, the moment I introduce lambda, it's just scaling these alphas down, right? It's making something, a number which was 1 before, it's just making a number smaller than 1, right? And you can see that it will make this number smaller than 1 for those DJs where those DJs are smaller. So let's say there's one. Let's say D1 is equal to 0.9, and let's say the 10 is 0.1. Okay, which one will be scaled more? Let's say I take lambda to be 1. Okay, some numbers I just. So then it's 0.9 square divided by 0.9 square plus 1, and this is 0.1 square divided by 2.1 square plus 1. Okay, it scales down this number. This number is further away from 1 compared to this number, so it's scaling down those coordinates of the B matrix, or this B diagonal matrix, which are smaller. Okay. Now we will interpret what those coordinates of the B matrix represent in terms of our data, because B was the SVD, it's part of the SVD decomposition of the data X matrix, right? So you can understand. So here all I'm explaining is that lambda influences these coefficients, which are the coefficients of the the coefficients of the columns of the U matrix. Okay. So this lambda influences the coefficients in different ways depending on the magnitude of D. For higher D values, it doesn't scale it that much compared to for lower D values. And now I'm going to tie it back to what does B's mean for the data matrix, because D was just a part of the SVD decomposition of the data matrix X, right? Okay, so let's do that. For that, let's look at something else, which is called PCA. How many of you have heard of PCA? You've heard of PCA, but you've not heard of SVD. Is that correct? Okay, so what do you remember about PCA? Maybe not the mathematics, but what do you remember about PCA?
It used to reduce the number of dimensions.
Yeah, it's used to reduce the number of dimensions of your data. Somehow, we'll get to that. Like precisely how it does that. Okay. Is PCA used to convert a matrix into an orthogonal matrix? The principal components are orthogonal, maybe? Yeah, we'll see what are principal components, and maybe they're orthogonal, maybe they're not. We'll see that. Okay, so PCA is pretty much SVD. So PCA is only applicable for a square matrix, whereas SVD, which I just defined, is applicable for the n cross P matrix. Our data matrix is not square, right? P is not related to n, the number of observations. Okay, so we're going to look at PCA of a specific square matrix. It's going to be X transpose X matrix transpose X matrix, which is going to be P cross P dimensional, right? Any confusion here? Let's look at the PCA, and it happens to be that the PCA is expressible in terms of the matrices that we saw in the SVD decomposition. In fact, the PCA is going to be B squared V transpose. Okay. So it's the same V which was on the right side of the SVD decomposition of X matrix. Okay, and it's the same B that was in the center of the SVD decomposition of the X matrix. Okay. Okay, one thing I kind of did not talk about when I started the SVD, the viewpoint of this regression is that let's assume that the X matrix is centered. Centered just means that for each column of the X data matrix, each column which represents the coordinate of the input variable, just remove the mean of that observation. Okay, so basically take the mean of these n numbers, like each coordinate of your input variable, let's say xj has a bunch of numbers, right? The n numbers. Take the mean, which is the sum of the numbers divided by n, and remove that number from each of the numbers. That's all centering means. Okay. It's an aside. It's not very important conceptually, but let's just do that so that I don't introduce other things. Okay, so I did so PCA of a matrix, a square matrix, is going to be written this way, and the V matrix. Sorry, I should put it. Yeah, the V matrix. Again, let's think of it in terms of columns. V1 to V. How many columns are there? P. Okay, it's a P cross P matrix. So V is P cross P, D is P cross P, and V transpose is also P cross P. Okay, remember this. D was P cross P before as well, and V was P cross P before as well. These vectors. So let's just introduce just I guess definition, phrases to call these vectors. So VJs are called principal component directions, and we'll just kind of, why did we introduce this notion of what is meant by principal, what is a component? We're just going to describe it through an example very soon. Okay, when we wrote the B matrix, think of let's assume that the B matrix, remember D matrix was D1, D2, and DP, right? Let's assume that D1 is greater than D2 is greater than DP. So I just ordered the diagonal matrix such that the first entry of the diagonal matrix is larger than the second entry of the diagonal matrix, and so on. Okay, just order them. So VJs are called principal component directions, and so why do we call it principal component direction? And it's because of this reason. So the reason is, let's focus on V1 for now. Let's just focus on the first column of this V matrix. Let's define another vector, okay, which is going to be X matrix times V matrix. V vector. So V was what? P times one dimensional vector. X is what? N times P dimensional matrix. X is always a data matrix. So V is going to be what? N times one dimensional vector, right? So this Z vector, the reason why VJs are called principal components, or let's say the V1 is called the first principal component direction, is because this Z vector, which is n dimensional, is the vector that has the largest variance among all linear combinations of columns of the X matrix. So what's happening? So I have this X matrix. Each column is the n observations of each coordinate input variable, right? My data matrix, each column is the observations, n observations of each coordinate input variable. If I multiply my data matrix with any vector from the right side, all it's doing is computing a linear combination of these columns. How many of you have heard of linear combination before? And I'm not sure what linear combination is. Okay, so I just described linear combination earlier for when I said think of this, I think I used alpha I ui as a linear combination of the columns of U matrix, right? So this actually can be written as U times alpha, where alpha is a vector with alpha is as the corresponding coordinates. Okay. So if you multiply any matrix with a vector, all you're doing is computing a linear combination of the columns of that matrix. Is just a fact. I mean, in the sense, we can actually expand out. Okay, let me do that. So I multiplied x with, this is an example 2. Let me do an example 1. If I multiply x with some vector v1, it just happened to be my, it's a special vector, we know that. But let's say, let's say it was some vector v1. Okay, let me not use v. Let me put it as alpha. Okay. So x matrix is n times p. Let me multiply it with some vector alpha, which is p times 1. Okay. Then, if you think of x matrix as x1 to xp, each column is n-dimensional vector times alpha, which is alpha 1 to alpha p. Okay. This is nothing but, you can just write the same thing as sum of alpha I times xi, where I is going from 1 to p, which means that you are just taking each column of your x matrix and multiplying each column with some coefficient alpha, then summing all the columns up. Column summing is just entry-wise summing of each row of the columns. Okay. So this is just a simple fact. So what did I say here? I said, okay, I did the PCA of my data matrix or data matrix transpose data matrix. I got some VB square V transpose. I'm just calling the columns of that V matrix to be my principal component directions. Okay. And in particular, I'm picking up V1. Okay. Why is V1 special? Because I said the diagonals, let me just order the diagonals entries such that the first diagonal entry is the largest. Okay. And so V1 is going to be special. And how is it special? If you right multiply my data matrix with V1, I'll get an n-dimensional vector. That is the vector that has the largest variance among all linear combinations of the columns of x. If you right multiply my data matrix, I'll get linear combination of my columns. But this special vector, is such that if I right multiply with that, V1, then the Z1 has the largest variance among all linear combinations of my data matrix. Okay. Pictorially, pictorially, okay, and the vector Z1 is called the largest principal component. Okay, Z1 is called the principal component. When you use just the principal component, it's an n-dimensional vector. And if you call principal component direction, it's going to be a d-dimensional vector. But the V vector is not very important. The Z vector is important. So this is the direction of the largest variance in this data set. Okay, this is a two-dimensional data set, and we're just asking in which direction is the variance the maximum. Okay, direction is just given by a vector direction. Right? Two-dimensional space, you can say certain direction, may have variance. You can see that in this direction, let's think of this direction. The mean, like if you can project all the data points on this direction, so you can always project points onto a line in 2D. Okay, you just squish all the points so that they fall on this line. Okay. The mean of that, once you squish the points, you have new points. You can take the mean. The mean will be somewhere around here. And if you look at those points, they're well spread out, which means that they have high variance. Okay. Right, they're spread out. All these points. Let me just illustrate that here. Again. Okay. There are a bunch of points, right? So I said this is the largest direction in that space. So these are the points. Okay, let me put the points on the line. Maybe they happen to be corresponding to some circles somewhere, right? Okay, I just squish these points onto this line. All I'm saying is the mean is somewhere, and you can see that in that one dimension the variance is high. Okay, if you compute the empirical variance, from this mean, there's a bunch of points very far away from it. So if you compute the empirical variance, empirical just means, sum of the squares of the distance of the points from the mean of the point, right? If you remember the definition of variance, it has high variance, that's all. So the Z1 that we computed using just linear algebra is actually, in 2 dimensions, is just actually this vector, a vector in this direction, okay? So, yeah?
V1 is a small vector, right? So it has smallest values among their matrix.
V1, no, V1 is just the, you're talking about V or Z? Sorry. No, V is the one of the columns of this, in the PC of X transpose X, it's just the first column.
So that D1, D2 to D2.
Yeah, I said D1 is greater than, here D1 is greater than, D1 is greater than, D2 is greater than, D3, whatever, so. I mean, that's just for some ordering. All I'm saying is, if you fix this ordering, I can talk about the largest component, so largest, okay, I don't want to do another expansion of this. It's basically, okay, I'll just write it. Okay, this is example 3. See, when I said, X transpose X is written as B square B transpose, all I'm saying is this right hand side can be written as sum of D I square, because D was individual, is a diagonal matrix, right? Sum of Di square times Bi transpose, okay? So it just happens that I said if D1 is the largest, let's just focus on D1. It just happens that if this matrix has this decomposition, then there is a matrix corresponding to D1, and that matrix is defined using D1. So let's focus on D1. So all that ordering is telling me is just focus on one of the components, V1 or VP, for example, right? I just pick V1. Yeah, I mean VP will be the smallest one. I mean smallest in some sense. Like you can talk about if D1 is largest. I'm just saying V1 has some interesting property, and I just describe what property it has, right?
I don't get how the variance is increasing if we put the linear combination of a small quantity into this X.
What is meant by small quantity? This is a vector, right? This is a p-dimensional vector. Just comes from the PCA, or this decomposition of this square matrix, okay? Right? I'm just saying if you multiply the vector with your data matrix, you'll get another vector which is n-dimensional. It just happens to correspond to the direction which has the largest variance in your data. Okay? Any question? Confusion? I think it will take some time for you to internalize a little bit of this discussion. But so why did I bring in SVD first and then PCA first? In SVD version of the problem, you saw that we had dj square by dj square plus lambda as the coefficients, right? So okay. So I said Z1 is the direction, I guess. Yeah. I mean, I said Z1 is that linear combination of your columns of your X matrix which has the largest variance. So Z1 is the direction. Okay. With largest variance in the data. Pictorially, I just showed you that. We can actually compute the variance. That variance is going to be variance of Z1 is going to be equal to D1 square divided by n. Okay. We can just do this, but this is not an important fact. All we're saying is that the principal component's variance is actually just depends on D. Okay. The entry of the diagonal matrix pretty much tells you what the variance in that direction is. Okay. And so, what is ridge regression doing? It's doing something like this, right? It's doing di square divided by di square plus lambda. right? There was that term in that expression that we saw, 2 minutes ago. So actually I should also write V1, it turns out, is equal to D1 times U1. Okay, remember U1 as an n cross 1 vector, D is just a scalar. So it turns out that the principal component happens to be just the first column of your U matrix in your SVD. Okay, it's those real relations, but intuitively just understand that V1 is the direction of the highest variance. Okay, so you see that when this regression lambda is non-zero, it's trying to kill. If you remember the predictions, the x times beta hat that we were looking at, that y hat, the y hat vector, we said it was some sort of a linear combination of ui's, right? The columns of u. Remember from a few minutes ago. And this is actually one of the scalar components which contributes to the alpha I. Is this? Yeah.
So is the larger variance related to the inputs having less collinearity with each other?
You just plot the in 2 dimensions. It's if it has more collinearity, if certain let's say a couple of feature dimensions have collinearity, then they will correlate. Like you'll have a band type of a thing. Yeah.
So if the values of V that have larger central variance are penalized less, is that related to trying to penalize variables that are less collinear with each other? Is that related to that at all? To try to collinearity?
The interpretation is like if you look at so the question is. So you're talking about how does collinearity impact what ridge regression is doing, right? You want to understand the relation. So you can think of in this plot, if x1 and x2 are collinear, you have you'll just have a diagonal line, right? Like, because now let's say x1 is equal to x2, then you just have line, right? They are perfectly collinear, let's say. Then you basically want to kill. Then you know that there's only one degree of freedom. So there's only one direction of variance. So if you think of all the green points lying on this one line, then there is one direction, which is the principal component direction, where there is variance in the data, and there is no other direction. The other direction doesn't even have any variance. The variance in the other direction is 0. Right? Like in this data. If the variation in the other direction is 0, then you wanna, then you wanna kill that direction. Basically, if the variance is already very close to 0 or almost 0, then that direction is not telling you anything about predicting y. So what is ridge regression doing? It's actually taking the linear combination of u vectors, which is just u vectors are the same as the principal component vectors. So this is the first u1 vector and this is the u2 vector in this case, and the coefficients, if there is less variance in the second direction, it's already the variance is captured by d, and I'm doing d square by d square plus lambda. So for any large lambda, that's even killed. Okay, so you're only basing your prediction only on the direction which has variance. Okay, so if it's perfectly collinear, the d itself is 0. Okay, so d by 0 plus lambda is 0 by 0 plus lambda is also 0. Okay, so it's very nearly collinear. You are killing the second direction. So you are killing the collinearity problem using this regression. Okay, because if you look at that expression, we said these are the directions of variance, and if things are collinear, because I've introduced this alpha term, some directions will get killed. Okay, only one. If two variables are collinear, one direction will be picked, the other direction will have very little variance, that will be killed because of lambda. Okay, that's just the other interpretation. Okay, so now let's look at LASSO. LASSO doesn't have so much of explanation, so this is the SVD viewpoint for what is lambda doing for ridge regression. Okay, and the reason I introduced this is also to introduce a couple of other tools. We kind of had a first brush with SVD first brush with principal component analysis. And we will revisit them again. These are nice techniques. I think some of you pointed out something to do with dimensionality of the data and reducing the data or something like that. We will revisit what those interpretations are a few lectures from now. But here we just use them as a way to understand what is lambda doing, okay, in ridge regression. Fine? So now let's look at LASSO. So LASSO has it's an abbreviation for least absolute shrinkage and selection operator. Okay, and what each of those terms mean is not very important, so we're gonna ignore it. It's some historical reason. But LASSO is very similar to ridge regression. It also kind of modifies the vanilla residual sum of squares. Okay, and it's going to be y vector minus x beta. So this is the usual thing. But now you have a lambda times sum over j is equal to 1 to p of the absolute values of beta j. Okay, so I'm gonna now penalize not the sum of the squares of beta j's, right? If you remember in ridge we are doing sum over j is equal to 1 to p of beta j square. That's what beta transpose beta would evaluate to. Here we are just changing it to something else. Okay? Yeah. So the choice of lambda you can make through cross validation. Whichever lambda works, it could be as good as 0. So sometimes lambda is equal to 0 may be the right lambda to set because all the individual coordinates of the input variable are actually relevant and useful to make predictions. Okay. Sorry, if you set it to infinity, you get beta to be 0, but then they'll have pretty much no explanatory power. Like only your intercept may have to explain everything in your data, right? So it's something you need to search using cross-validation. Yeah, I guess the jump from subset selection to ridge regression is that in subset selection you had discrete choices, a finite number of choices, like 2 to the power p minus 1, whatever. The number of subsets that you can see is some finite number. Whereas here lambda seems to be a continuous one-dimensional parameter that you need to kind of vary over. Maybe just take, some, exact, just break down the range of lambda into intervals and just pick few lambdas. Okay, like lambda can be 0, 0.1, 0.2, 0.3 to 1 or something. It depends on your application, but yeah. So you have a finite number of lambdas to check for and choose among. Okay, so this is also called L1 penalty, and the ridge one is also called L2 penalty. Okay. Why L1 and L2? It's again comes from, if you've done a course on analysis or something, comes from some sequences of numbers, but we don't care. Okay, so it's just a definition of what does penalties mean. The reason, so ridge regression we could kind of think about it a couple of times in depth because we had a closed form expression for the beta hat. Here, unfortunately, there is no closed form expression for beta hat. Let me subscribe to LASSO to just call it. There is some beta hat, bunch of coefficients, which minimizes this RSS lambda beta score for a fixed lambda. Okay, like I pick the lambda, I can score every beta with this objective, and I get a beta hat, right? So I don't have a closed form expression for that. Okay, so how do you compute it? You use basically tools for optimization. In particular, it happens that this objective is nice. It's called the technical term in optimization field for this is just it's called convex. Okay, the objective just happens to be a nice convex objective. Okay, since it's nice, it happens to have a single optimum point. It looks like a, I don't know how, okay, we'll actually look at how it looks like, but it's a nice objective to optimize for numerically. So all I'm saying is, for linear regression and regression, we have closed form expressions. For LASSO, we don't have a closed form expression, but we can optimize for the best beta hat numerically, and that optimized procedure, whatever the algorithm to get to beta hat, it's not difficult. It's a nice, since the objective is nice, we can kind of do that. Okay, find the best beta hat easily. Okay, so there's actually a picture. So again, lambda is again a choice that you need to make. So here we are seeing the choice of lambda as a function of something like shrinkage factor, but think of this as a lambda, okay, inverse of lambda. Again, similar to, you remember the previous plot, again I had inverse of lambda on the x-axis. So you can see that when lambda is very close to 0, or actually 0, you have a bunch of coefficients. So this is again the prostate cancer prediction example. I have a bunch of coefficients like LC eval has a coefficient value of maybe 0.7, positive 0.7, maybe LCP has a coefficient value of -0.3. When lambda is almost 0, okay? I think at 1 it's actually 0. And the moment I started introducing lambda, now the penalty becomes effective, right? When lambda is 0, it's just linear regression. And when lambda is non-zero, it's becoming the penalty is becoming effective, and some coefficients are actually jumping to 0 faster than the others. So for example, Gleason is going to 0 immediately, okay, for some slight positive value of lambda. If you crank up lambda all the way to some large number, then all the coefficients are 0. So they all touch 0, like all of them got touched to 0, and at this point lambda is very large, so all the coefficients are 0. Okay, so it is somewhat mimicking subset selection, a soft version of subset selection, like it's killing some coordinates of your data, okay, because it thinks it's not useful for, it's optimizing for that objective for different lambda. So for every lambda, it says that some coefficient should be actually set to 0 for that objective RSS of lambda comma beta to be small. Okay, so this is in contrast with ridge regression. If you remember ridge regression, all the coefficients went to 0 at one of the points. They were becoming small, they were shrinking, but they were going to 0 at 1 when lambda was really large. Here, even for intermediate values of lambdas, like at this point, for example, at this point 4 or a little bit less than 0.4, 5 of the coefficients are 0 and 3 of the coefficients are non-zero. Okay, at this very light vertical dashed line. Okay, so that's the, again you need to choose lambda. You do cross validation to choose this lambda value. Okay. There's actually a okay. So just to give you, drill down what exactly is happening with LASSO and linear regression, because the only thing we changed is the second term. We just changed from sum of the squares of beta I or beta j to sum of the absolute values of beta I, right? Remember, I think I just wrote it here. Yeah, the only thing we changed is Ridge had this expression, and for LASSO we changed the expression to that. Okay, and it had a different behavior as a function of lambda, right? We can actually try to visualize what these penalties are doing, okay, through a two-dimensional example. Okay, and so let's say difference between and LASSO. Okay, so we're gonna kind of understand this from a two-dimensional example. So what was the difference that we observed? So for Ridge, we saw that LASSO, we saw that for some of the coefficients are actually setting to 0. some of the beta j's are being set to 0. Beta j's are set to 0. Here which also beta j's are set to 0, but for very large value of lambda. Okay, all of them together are set to 0. So imagine I'm just trying the same data set, and I'm just replicating the same data set. So what do I mean by same data set? So what does this look like? These are top views. So these concentric ellipses represent the level sets, or they just represent the first term of the RSS. Okay, what is the first term of the RSS? So it was just the sum of yi minus xi transpose beta square, right? This was basically something like this, right? This is actually a quadratic function of beta. Okay, so if you think of this is actually now x and y are not x1 and x2 in this two-dimensional example. X-axis is actually beta 1, y-axis is beta 2. Okay. I just drew two pictures, okay, because I wanted to illustrate both LASSO and regression. So if you look at this, it's just a quadratic function of beta. It just means that ellipse is actually like a quadratic function. Like when you define an ellipse, you kind of define a quadratic function of the in two dimensions is going to be like actually let me write down an expression for an ellipse, although we won't need it. It's like let me not use x, like z1 by a1 plus z1 square plus a1 and z2 square by a2 is equal to constant or something like that. Okay, this is like the definition of an ellipse. So these concentric circles just mean that the first term looks like from the top view. If you chop the first term, which is the RSS term, at different levels, you will get concentric circles. It just means that a beta 1 value here and a beta 2 value here will give the same RSS value as a beta 1 value here and a beta 2 value there. In the sense, the RSS value, for example, 10 units, okay, sum of the squares of the yis minus xi transpose beta, in two-dimensional case, it's just beta 1 and beta 2. For two different values of beta 1 and beta 2, you get the same RSS value. Okay, these are just concentric. These are called contour lines in mapping. For example, if you've seen maps, you've seen these kind of contour lines. They are at the same elevation. Okay, so this picture is just drawing the elevation. It's just drawing this loss function, and it's just showing it as it's a quadratic, so it looks like an ellipse. And these are the concentric lines at different levels of this, different values that the RSS can take. Okay, and ridge, what it does is it tries to. So ridge, I'm going to draw it as a circle. Okay, what is it I'm drawing? So the first concentric circles were for the first term. The second circle is for the second term, which is sum of beta j square. Okay, j is equal to 1 to p. Okay, this resembles, what does this resemble? This resembles the definition of a circle, right? Remember, circle is x, let me not use x, z1 square plus z2 square is equal to some other constant, right? If you remember in 2D, a circle is x square plus y square is equal to constant, right? So the second term for in regression, so both ridge and LASSO are the same first terms. So that's why I wrote some concentric circular things, concentric ellipsoidal things over there at the top. And for ridge, I drew a circle because the ridge penalty looks like a circle. And lasso penalty, it happens that it looks like a diamond, okay, or a rotated square in 2 dimensions, okay. If this is just the sum of beta j, absolute value, j is equal to 1 to p. I mean, I'm just setting this to be some constant, okay, some constant. I don't want to write it because it will be confusing. At some constant level, it looks like a diamond, one looks like a circle. And all regression lasso are trying to do is balance these two objectives. So you want to find a beta, which, if you did not have these second terms, which are these penalties, the best beta would be the center of these concentric circles, okay, which will be the same solution. Think of the linear regression objective as a quadratic objective. It's like a ball, and there is one beta value which is at the bottom of the ball, okay, that's at the center of these concentric ellipsoids, okay. And all these additional penalties are doing is, okay, this is no more a good solution, try to find a solution which is closer to this circle or inside the circle, okay. We're trying to balance between two terms. The first term, which says that, which gives me the vanilla linear regression coefficient, is the best estimate of betas, and then the second term is penalizing betas to be large, right? It's saying betas being zeros is a good idea, right? Here it's saying the sum of the absolute values of beta should be small. Now what happens is, geometrically, pictorially, the right trade-off between these two is when this concentric circle touches the circle, okay, the circle relating to the first term, the ellipse relating to the first term touches the circle relating to the second term, okay. And similarly over here, okay, somehow it touches, okay. I drew it I'm trying to suggest something, which is that sometimes on the lasso side it can touch at the corners of this diamond, the corners of this rotated square, and at the corners one of the coefficients is going to be 0, okay. One of the, like at this corner, beta 2 is equal to 0, right? And that's why you get 0 coefficients in the, when you looked at this diagram. You got some 0 coefficients early on, because in a 9-dimensional or 8-dimensional space, there's a huge 8-dimensional diamond, and when you're intersecting the diamond with concentric ellipsoids, it happens that the ellipsoids touch the diamond at the corners in this case, okay. It's just a geometric interpretation of what's happening, what's the difference between lasso and regression. Any questions? Or did somebody understand something about this?
So the area in the lasso curve regression, can you say that the lasso thing is more constructive than regression?
What do you mean area? It's just 2 penalties, right? No, I mean it's not about areas. I mean, so think of same lambda. So let's say I only choose lambda, right? So think of the same lambdas. So if it's the same lambdas, then this diamond, this square, for example, can be of unit length. So for example, the blue region on the y-axis here maybe is 1 unit, and the blue region on the y-axis here is also 1 unit. So it's not about areas, it's all about how are the 2 penalties, like you want to find a beta which satisfies, which kind of gives a low number for the first term and a low number for the second term as well, right? So you're trying to balance them, and it just happens that when you try to balance them for lasso, some of the terms have to be 0, like because it's a diamond, because it has sharp corners, whereas the ridge regression, because it's the sum of the squares of the betas, it looks like a circle, and so there are no sharp corners, so you'll have non-zero beta coefficients when you intersect, when you try to balance these 2 objectives. Okay, this is just a top view of the objectives. Like one objective will look like a ball, which is this concentric thing here, and the second objective, beta, the second term in the ridge regression is like a sum of the squares, so it looks like a circles, concentric circles. Yeah.
What is the purpose of introducing penalties to move them to
So the purpose of the penalty is to do a soft version of subset selection, right? In subset selection, we're dropping coordinates of the input variable. Here we are not. Here, for example, ridge regression has the same effect, right? It's dropping coordinates. For a certain lambda, for example, like this lambda, it drops 6 coordinates. So it is actually doing, like, you can replace subset selection with LASSO, okay? Or you can replace subset selection with ridge regression. So in both cases, I'm trying to explain what does it mean by, I mean, there's soft versions of subset selection, so they're not dropping the coordinates, so what are they doing, right? In ridge regression, it happens that they are scaling the diagonal entries of the SVD diagonal matrix somehow, which is related to the variance in the data and so on. In ridge regression case, the lambda is actually killing some of the coefficients to actually setting it to 0, because it happens that the second term seems like a diagonal geometrically, okay? And you can actually verify this. The absolute value of you can check that this diamond here is the shaded region here, blue region, is actually equal to sum of absolute value of x plus absolute value of y equal to 1, for example, is less than or equal to 1, okay? And this shaded region here is exactly corresponds to the definition of a circle. It's like x squared plus y squared is less than or equal to constant. If you want to share it inside, it's less than or equal to constant. It's exactly a circle. It's x squared plus y squared is equal to 1, let's say. That's the circle. And we'll get down here. That's the, I hope you got some of what I'm trying to say. It's not, so the thing is, somebody may ask you, why do you want to use LASSO, why don't you use ridge regression? You need to say something about why you made one choice or the other. They may say, why don't you use just subset selection, okay? There may be pros and cons for each one of them, so by understanding some geometric picture and some impact of the choice of lambda and so on, you can kind of reason why one may be interesting to use versus the other.
If we started discussion with, like, we should have simple and accurate models, but if we start introducing this is ridge and LASSO, I would say it's still considering most of the variables and slowly, like you said, softly cutting out variables.
Yeah.
But subset selection is more of selecting, let's say, 2 variables per time. That basically corresponds to a simpler but accurate model as Then why is the question of LASSO and coming on in terms if we are looking for simple and accurate models? Why subset selection can help us in that?
Yeah, so if it is truly the case that, let's consider a 10-dimensional data set where only 2 dimensions matter for predicting y and everything else is irrelevant, they're basically noise, okay? Then doing subset selection probably is the best bang for buck, but that requires this additional knowledge that these additional coordinates are noise, right? But you don't know a priori whether they are useless or not, so therefore you have a choice to make whether you want to go with subset selection or ridge regression or LASSO. So the only thing you have is data, right? If you have the joint distribution, you can do everything. I think I've been repeating this multiple times. If you have the joint distribution, you can exactly compute the conditional expectation of y given x is equal to x. Like if you want to minimize EPE, which is the square loss, you can compute expectation of y given x because you know the joint distribution. This is just expectation definition, plug in some integral or some summation, and you can be done. There is nothing else to do for prediction or classification. But the moment you only have data, then you either have to assume something more or you want to delicately deal with this. That's what we are doing here with subset selection, ridge regression and LASSO. Okay?
When we talk, say, in subset selection, we draw 5 variables, and in LASSO, we choose the lambda, which is dropping 5 variables.
Yeah.
How is it different?
They may give you different coefficients, yeah. Yeah, the effect of choosing a lambda where the effect of those procedures where when they have dropped 5 coefficients will be the same. I mean, so, well, the coefficients can be different because LASSO is actually having additional penalty term, whereas within the subset selection it's just looking at linear regression term only. So if you drop 5 variables and minimize just the linear first term, you may get some beta hat, but we drop 5 variables and just evaluate which beta is the best for LASSO. It may give you a different beta hat, but yeah. there is no relation, so you cannot say which one is better over the other. The only way you can test it is through validation, because you only have data. We can say which is better or not if we have the joint some information about the joint distribution. Okay. If we don't, then we can't say which is better.
This extension of another question of this.
Yeah.
Like between lasso and ridge, we can't decide beforehand which to go.
We can't decide between lasso and ridge beforehand. So, for example, lasso is preferred because I'll give you settings where lasso is preferred, where you have really lots of measurements. Okay. Then you probably think that most of these measurements are probably noise. Okay, then that means that these coefficients should actually be 0. Okay, and then you may prefer lasso because lasso induces some of the coefficients to actually be 0, whereas ridge may keep the coefficient 0.01, 0.02 or something like some small values which are non-zero. So in high dimensional settings, these are settings where the number of dimensions, number of features is like 10,000 or 100,000 or something like that, which is true. For example, in Google's case, for example, they actually have millions of X-ray coordinates for example, some prediction problems to solve. And for that, lasso may be a good idea because they really know that there is a very small, and out of million coordinates, maybe 1,000 are actually useful and everything else is useless, and maybe use lasso. Okay. Instead of doing subset selection, maybe a million choose 1,000 probably is not a it's a really large number. But in general, you cannot say one is better than the other. Okay, I have 7 minutes. I wanted to introduce classification. So how many of you are up for classification right now? Okay, so actually I will introduce classification next time. Although it uses the same linear regression, so you can actually, if you remember in the first lecture, we said we can use linear regression for classification if we kind of are cognizant of the fact that the G, I can use Y for a G, but remember that there is no relationship between G. For example, cats versus dogs, I can say cats is +1, dogs is -1, and I can say Y is equal to +1 and -1, and now I have a quantitative variable, I can just do linear regression. But you have to remember that there is no ordinal relationship between cats and dogs. Like Y is cat +1 and dog -1, it can be the opposite direction, right? That's the only caveat while using linear regression for classification. So we will discuss that next time. And with that, we are done with linear regression and all its important variants. There are many other variants which you may come across later, and then we'll just focus on what is the issue with classification, why is it different from regression, and look at logistic regression, which you might have already seen before, but this one will be more detailed. Yeah. Okay, thank you.